Hi all. In last videos we saw the derivation of the Reynolds stress equations, the appearance of Reynolds stresses in Reynolds stress equation. These additional terms called Reynolds stresses has to be closed, and we used zero equations model like algebraic mixing length model, k epsilon 2 equations model, and finally we directly model derived six equations each for Reynolds stress terms, and those equations are coupled partial differential equations that has to be solved along with the epsilon equations to identify this Reynolds stress to compute mean flow values using the Reynolds equations. So, however, we also identify its limitations, like it is computationally expensive and it's not that validated as similar to K epsilon model. And there are certain still those equations are solved directly. The appearance of equations have some limitations in flows like unconfined recirculating flows. Here, Rodi proposed an alternate way of Reynolds stress equations where there are certain effects like convection and diffusion terms which gives you a computationally high cost can be neglected, and once those terms are removed we can end up in giving we can ended up Reynolds stress equations are reduced to a system of algebraic equations uh, based on 3.52, where on the so based on this 3.52 we can develop an algebraic stress model similar to 3.53 instead of having a partial differential equations neglecting the convective and diffusive effect. uh, there are certain flows where we can neglect those diffusive and convective effect, and irrespective of that we can still capture the anisotropic effect of the Reynolds stress in the flow equations. So this is the concept idea behind bringing up this algebraic stress model, which is derived from the 3.52, invoking the concept that relations between the turbulent kinetic energy, uh, the convection diffusion terms in the Reynolds stress is proportional to the sum of the convection and diffusion terms of the turbulent kinetic energy. So based on this concept, this equation, six equations coupled nonlinear algebraic equation are derived, and this can be solved using a standard nonlinear iterative methods. And to compute this, we need an k epsilon equation. So two equations with the additional these algebraic equations gives you Reynolds stress models. So it had a wide applications in when it was had discovered, but however later they developed nonlinear versions of the k epsilon model. So once these nonlinear versions of the k epsilon model came into effect, capturing the anisotropic viscosity, this algebraic Reynolds stress model lost its popularity. So these are the advantages because it accounts for Reynolds stress anisotropy, but the disadvantage is not widely validated, similar to the mixing length and k epsilon model. And also the nonlinear version of the k epsilon model came into effect, and which brings both anisotropic and computationally uh, feasible k epsilon model. So this is all about. Now so there are certain recent advances developed based on two concepts. One is only development of this turbulence model only in particular application for a uh, for focusing on a particular limited category of flows. And the other research was happening that we have to bring up a comprehensive and completely general purpose turbulence models. But in this aspect only this first category develop up have given much focus on the industrial side, because most of the industrial sites are belong to a particular segment of flows like pipe flows in oil industries, and turbine and combustions are particularly for swelling flows. So this but despite that there were many attempts to make general purpose models, but unfortunately bringing up this general purpose model like the Reynolds stress model brings additional closer terms. For example, developing a Reynolds stress model bring additional terms like a third order moment, and this brings an additional empirical necessity to close this Reynolds stress models. And also recently they developed some kind of an extension to the K epsilon model, uh, which is something brings kind of a nonlinear effect into the K epsilon model. So these also have become one of the development happened during the later part of the turbulence theory. And also recently uh, the statistical theory being applied, and they bring up a new K epsilon model called R engineer normalization group based K epsilon model, which has become widely populated, especially in the CFD packages. So these are the modified version of the K epsilon model based on the knee normalization group theory from the research group of Yakut. So see, these are some of the recent advances related to the turbulence modeling, but we haven't covered some kind of other advances like LES model, which possibly will be covering in the later part of the lecture series. Thank you.